Welcome back. This video, and maybe the next, depends how long it takes, is all about Doppler radar modules, to be exact HB100s, the accompanying amplifier or breakout boards from Limpkin, and microcontrollers. I have an Arduino here. So, where should we start? Maybe with a little bit of theory about the Doppler effect these modules are based on. I will spare you from the mathematically and physically complete derivation of the Doppler effect equations, because that would take a better part of an hour. Instead, I'll give you a simplified, watered down version where I take a lot of questionable shortcuts, but in the end will arrive at the prevalently used Doppler radar formula. Okay? And to be exact, when I'm talking here about the Doppler effect, I'm talking about the classical Doppler effect. Classical as in classical mechanics, not about the relativistic Doppler effect according to Einstein's theories of relativity. So let's assume we have here a wave source. It doesn't matter if it's radio wave, lights or sound waves, that's transmitting with a frequency f transmit. And then we have a receiver here that will receive the wave with a frequency f receive. If our transmitter and our receiver are not moving relative to each other, so the distance between the two stays the same, then of course the received frequency is equal to the transmitted frequency. Now, our waves have a certain wavelength, lambda, and a certain speed, c. C here not necessarily being the speed of light. If that's sound waves, then it's the speed of sound in the atmosphere or in the water or whatever. And you've probably seen these formulas before. This is just the relationship between lambda, the speed c, and the frequency. So the wavelength lambda is the speed over the frequency of a wave, and the frequency of the wave is its speed over its wavelength. Now let's get moving, and it doesn't matter what is moving, if just the transmitter is moving or the receiver is moving or both are moving. All that matters is the relative velocity, which can be positive or negative, between the transmitter or the receiver. Two examples. Let's assume for the moment that our transmitter is stationary and our receiver is moving towards the transmitter with a certain speed. Then from the view of the receiver, our waves certainly move faster. To be exact, we have to add the speed of the receiver to the speed c of the waves. And what happens if c increases and the wavelength stays the same? The frequency increases. Or if the receiver moves away from our transmitter, then to the receiver the waves appear to be smaller. To be exactly, the velocity of the waves minus the velocity of the receiver. And as the velocity, the apparent velocity to the receiver is getting smaller, the frequency is getting smaller. Let's put some math where my finger was. We already talked about that formula here. So the frequency is equal to the speed of the wave divided by its wavelength. And if you put all the explanations I gave you before into that formula, you get that the received frequency is equal to the speed of the wave plus minus the relative velocity between the receiver and the transmitter, below here somewhere, divided by the transmitted wavelength. Back to my examples. Let's assume that the wavelength of our wave is 1 and its velocity is 2, both completely dimensionless, okay? And we have no relative velocity between our receiver and our transmitter below here somewhere. Then our frequency is, that formula, completely unmodified. The speed 2 over the wavelength 1 equals a frequency of 2. If our receiver now moves towards the transmitter, let's say with a relative speed of 1, then we get, with that formula, 2 plus relative speed of 1 over the wavelength of 1 equals a frequency of 3. And if it moves away with a relative speed of 1, then we get, according to that formula, 2 minus relative speed of 1 over the wavelength of 1, a frequency of 1. And you probably immediately saw why I choose a wavelength of 1. If we take that formula here, so the wavelength is equal to the speed of our waves divided by its frequency, and put that in here for the lambda transmitted, we get that. So our received frequency is equal to the speed of our wave plus minus the relative velocity transmitter to receiver over the speed of the wave divided by the transmitted frequency. And if we rearrange that a little bit, we arrive at the classical Doppler formula. The frequency received is equal to the frequency transmitted times 1 plus minus the relative velocity between receiver and transmitter over the speed of the waves. If you just want to know the difference between the transmitted and the received frequency, so the delta F, then you simply take the transmitted frequency minus the received frequency from here, rearrange that a bit, and you arrive at that formula. So delta F is equal to plus minus, that should be minus plus, the transmitted frequency times our relative velocity divided by the speed of our waves. But wait, we are talking about a Doppler radar. So our radar is sending out these red waves and they are reflected by some object, and that object sees them frequency shifted according to our formula, and it reflects them back at that frequency to the radar receiver. But there's still velocity here, so the radar receiver sees them again frequency shifted. In effect, we have to double our relative velocity between the radar and the object reflecting the radar wave in the formulas. And so here, instead of V, you find always 2V. That's the formulas for the Doppler radar. That were the formulas for the Doppler effect. You also find one of these formulas in the application notes for the HB100 radar module. If I can find them again in the internet, I just have a copy here, put a link in the description. Anyway, they write it a little bit differently here, but you can see, but for that cos phi term, and we talk about that in a second, it's basically our formula here. So there's the ft, there's our speed of light c, and there's our 2 times the relative velocity between radar and the object. For reasons that will become clear later, they also drop the plus minus. One more remark on the speed of light, which is given here at 3 times 10 to the power of 8 meters per second. In vacuum, it's exactly that number, and where we are living currently in a standard atmosphere at 25 degrees C and 1013 millibars, it's even a little bit slower, that number here. But now let's talk about that cos phi term. I was always talking about the relative speed between the transmitter or Doppler radar and the reflecting object or the receiver, along a straight line connecting them. They are talking about a stationary Doppler radar and a reflective object traveling at a velocity here at an angle phi to that straight line. And that simple trigonometry, the speed component of the total speed of the object that really goes towards or away from the Doppler radar is simply calculated by that velocity times cosine of that angle phi. That's all. Since we're already talking about stuff from the application notes for these HB100 radar modules, we might as well move on to these little buggers. They are surprisingly simple devices. So they need a 5-volt supply and they contain an oscillator which oscillates in the X-band, so about-ish 10 gigahertz, which is built around just a single transistor. And these 10 gigahertz are transmitted via a patch antenna. These patches here. On the other side, you have a patch antenna for receiving the reflected radar waves. And both go into a mixer. The oscillator output is, of course, attenuated properly. And the output from that frequency mixer goes to your intermediate frequency output. That's all. By the way, the mixer also consists of just one transistor. Please note that I'm not using original HB100 modules, but some Chinese clones, which are marked ZH100. And if you compare the picture here in the application notes with that Chinese module, you see subtle differences. Nothing too great. But what I wanted to point out is that this one ground connector here is offset 0.1 inches to the other ground connector. That will also bite us in the behind as soon as we start using these Limpkin breakout and amplifier boards for the HB100 modules. But now let's play a little bit with such a module. So I connected it to a 5-volt supply, and by the way, unboxing video for that over on P4305 card link. And I connected the oscilloscope to the intermediate frequency output. And the first thing you notice is that the intermediate frequency output has a DC offset. And it's already working if I move my hand here. A DC offset of about-ish 125 millivolts. And it's quite noisy. So the noise level is 50 millivolts. One division here is currently 50 millivolts. On the voltage axis, and on my time scale I have 50 milliseconds per division. And if I wave my hand, I get a signal out of it. But maybe we can do a little bit better. So I will try now to wave my hand with approximately 1 meter per second in front of the sensor. And I have here 1 meter 20 distance to the sensor to 20 centimeter distance to the sensor. So let's try that. 21, 21, 21, 21, 21, 21. And you can see a signal, but it's not really big, huh? Especially if I'm a little bit further away. Let's try something else, and I take here some metal, a much better reflector. So 21, 21, 21, 21, 21, 21. Yeah, a much better signal, yeah, much more reflective radar target, but still a very low level signal. So what we've just seen here, that was in the order of magnitude of 100 millivolts at most. So yeah, and that's where these amplifier boards come in. But yeah, first let's talk about what exactly is the frequency that's coming out of here. And for that we first have to talk about that mixer that mixes the transmitted frequency with the received frequency to give us that intermediate frequency output. A frequency mixer or radio frequency mixer, RF mixer, is ideally just a multiplier. That is, it multiplies both input signals, and the result of that multiplication is our output or our intermediate frequency signal. Let's consider these two input signals here, and yeah, to simplify things, I took square waves, and our time scale here from start to end is 1 second. So I have here a 4 Hertz signal that has exactly 1, 2, 3, 4 cycles in a second, 4 Hertz, and a 6 Hertz signal, the green line. So 1, 2, 3, 4, 5, 6 cycles per second. And to make things even more easier, let's consider signal levels here at the top of +1 and at the bottom of -1. Volts, millivolts, whatever. So if we multiply both these signals, 1 times 1 is 1, 1 times -1 is -1, -1 times -1 is 1, and yeah, 1 times -1, yeah, the same is -1. And we come to that curve here if we multiply both. And if you look closely at that signal, you see that it has here a rhythm of, 2 cycles within a second, so 2 Hertz. So we have that one cycle here starting at high, grizzle, grizzle, low, grizzle, grizzle, high, and that repeats. High, grizzle, grizzle, low, grizzle, grizzle, high. So somewhere in here is a 2 Hertz signal. And that's exactly the difference between our 6 Hertz and 4 Hertz input signal. But yeah, we have also that higher frequency stuff, and according to the theory, that's 10 Hertz and is the sum of the frequencies of our input signals. So 6 Hertz plus 4 Hertz. Yeah, I leave it to you to find the 10 Hertz in here somewhere. Second example. We have again our 4 Hertz wave in black, and this time we multiply it with a 3 Hertz wave in green. So 1 cycle, 2 cycles, 3 cycles. And that's the resulting curve here. And you can see that pattern here. So we start high, grizzle, 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 low, grizzle, 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 high, and so on both sides. Repeats once every second. So our output signal or intermediate frequency signal is 1 Hertz, which is 4 Hertz minus 3 Hertz. And yeah, the grizzle here is higher frequency stuff. Again, it's the sum of our 4 Hertz and 3 Hertz input signals. That is 7 Hz. So our intermediate frequency output is a mix between the absolute of the difference between the two input frequencies and the sum of the two input frequencies. Usually you are only interested in the difference between the two frequencies and you filter out that higher frequency stuff in real-world applications. The fact that we only get the absolute of the difference between the two input frequencies out of our mixer is the reason that here in the application note they dropped the plus minus from their formula, because we don't get plus minus depending on if something approaches the radar and increases the received frequency or moves away from the radar, that is, the received frequency is decreased. We cannot make that distinction. Anyway, the formula we have already developed for Doppler radar gives us the delta of the frequency between the transmitted and received frequency depending on the velocity between our radar and our object. So exactly the output of our mixer, minus the plus minus, of course. And if we put numbers to that, then our delta F in my hand waving example was plus minus 10.525 gigahertz. That's supposedly the oscillation frequency of the transmitter here, times 2 times 1 meter per second divided by the speed of light in atmosphere, so I won't read that out, and that gives us roughly 70 Hertz. In the application notes you find that table here to make your life easier. So they already calculated speed of light and transmit frequency and that factor of 2, and they give you a constant to multiply with your velocity to arrive at your output frequency, your intermediate frequency. That table is in kilometers per hour, and I recalculated that for meters per second, and then that constant here for 10.525 gigahertz becomes 70.164. So our output frequency, according to the vendor, is 70.164 times the velocity in meters per second. We just calculated 70.235 per meter per second output frequency. The reason being that the vendor simply assumes the speed of light at 300 million meters per second, and I took the correct value for the speed of light in a standard atmosphere of 299,710,000 meters per second. Let's talk now about these Limpkin HB100 breakout, or better amplifier boards for the HB100 Doppler radar modules. We already know that the output from these modules is quite noisy, 50 millivolt noise level, and that the signal level itself drops out very quickly if I move my hand away. I'm a little bit off screen and my signal level is down to maybe 10th of millivolts, or if I go away a meter or so, single digit millivolt values. And these breakout boards are supposed to make sense out of these signals. Connection-wise, these boards are simple affairs. You have a pin header here at the back, you feed in VCC 5 volts, your ground connection, and you have a frequency out that should give you the processed, we will see that in a second, intermediate frequency signal from the HB100 radar module. And you have a V-out pin that gives you a DC voltage, which is kinda indicative of the signal level that goes into the board from the HB100 radar module. You have 4 more pin headers here, VCC, intermediate frequency, ground and ground, to connect your HB100 radar module. And they are, of course, soldered to the other side. That is, you simply fit your radar module on top of it. But there's a little problem. Remember how I told you that the ground headers on the HB100 are offset 0.1 inches to each other? That's of course to prevent the HB100 being plugged in the wrong way around in whatever breakout board you are using. However, on Limpkin's breakout board there is no such offset on the ground headers. So I had to improvise a little bit. I snipped off 1 pin at that header and stuffed it here in that hole. So you still have the insurance that you cannot put them together the wrong way around. But it's not that pretty. Anyway, let's connect Limpkin's breakout board to a signal generator and the scope and see what it can do. I dare not touch or move anything here, so I will pan a little bit to show you what's on the bench. Anyway, there's our HB100 breakout module from Limpkin. You can ignore the Nano here, it's not connected. I'm feeding in here the intermediate frequency signal from a signal generator, and I connected that 4-pin header to 5 volts VCC and the outputs also to the scope. Yeah, the intermediate frequency is also displayed on the scope, and if we have a look at the rest of the bench, yeah, there's our signal generator, here's our power source, and here's our scope. And I will now, I guess, just focus on the scope. I'm feeding into the intermediate frequency input a 10 Hz sine wave, 10 millivolts amplitude with a little DC offset of 125 millivolts. Yeah, also a little bit noisy, like we would get it from the HB100 module. And out we get a 5 volt square wave with exactly the same frequency. Isn't that nice? And the voltage output gives us currently, about 5 volts. So that would be the maximum signal level. Now let's turn down the signal amplitude here. Now I'm at 1 millivolts peak to peak for the sine wave, and we still get a square wave out. I mean, that's quite a feat, isn't it? Detecting the sine wave in all that noise. And our signal level dropped a little bit. Now let's change the frequency. So that's 10 Hertz,
20 Hertz, 30 Hertz, 40 Hertz, 50, 60, 70, 80, 90, 100, 110,
120. And you see the signal level is dropping. 140. And now it's dropping some stuff. Let's go back to 10 Hertz.
And 9 Hertz, 8 Hertz, 7 Hertz, 6 Hertz. You see the signal level is dropping again. 5 Hertz.
4 Hertz. Wow. And all that, with 1 millivolt input in all that noise. Let's have a look at the circuit diagram, how this black magic is performed. That's Limpkin's schematic for that amplifier board, and shouldn't I have mentioned it before, there is a link in the description to Limpkin's website where you find an excellent documentation for the whole thing, including the KiCad files, Gerber files so you can produce your own PCBs, principle of operation, simply everything. However, that schematic of his, and he admits that on its website, is not really easy to read. So I've redrawn it for your benefit. Anyway, VCC 5 volt comes in here, is filtered by a 10 micro cap, and then we have a little ferrite bead here for extra filtering, and then comes another 10 micro cap, so our 5 volt rail is really filtered to the death. Then we have this 1-to-1 voltage divider here, which gives us here a voltage rail, an additional voltage rail at 1/2 VCC, so 2.5 volts, and that's also filtered by a 10 micro cap. The intermediate frequency from the HB100 comes in here. There's a little 12K load resistor on that input. And then comes a decoupling capacitor 4.7 micro that filters out the DC component which we have seen on the oscilloscope. Now it gets interesting. This part of the circuit forms an active non-inverting bandpass filter. I won't explain the details about that part of the circuit here. Just look it up on the interweb. Active bandpass filter, and you get all the information you need. Anyway, that thing has a gain in the pass band of 100, a lower cutoff frequency of 3.4 Hz, and an upper cutoff frequency of 72 Hz. And I didn't calculate these numbers myself. I took them from Limpkin's documentation. Note that the input here is biased to 2.5 volts, half VCC, through that 330K resistor. So what we are seeing here at the input is a sine wave centered around that 1/2 VCC rail. And of course, at the output we have the same sine wave amplified 100 times, as long as its frequency is within the pass band. And that goes now into this circuit here, which is an inverting active bandpass filter. And the parameters here are gain of 121, lower cutoff frequency 4.1 Hz, and upper cutoff frequency 72 Hz again. And again, I took these values from Limpkin's documentation. I didn't calculate that myself. Anyway, we get an even larger amplified sine wave centered around the 1/2 VCC 2.5 volt rail out here. So in total, we have a second order bandpass filter with a gain of 12,100, quite a lot, a lower cutoff frequency of somewhere between 3 and 4 Hz, and an upper cutoff frequency of 72 Hz. Please note that we won't really see a nice sine wave here at that output. If you multiply 1 millivolt by 12,100, you have peak to peak 12 volts. That is the sine wave form here is probably capped off at 5 volts and ground. Then follows a simple peak detector, diode peak detector here, with capacitor, resistor, and of course the diode. That gives us that V out signal that indicates if we have a good signal level here. And finally, there's that comparator here that transforms our sine wave or our capped sine wave into a nice 5 volt square wave signal. And I'm not sure, to be honest, why the input here, the positive input, is not connected to the 2.5 volt half VCC rail, but has its own voltage divider here, which is not quite 1-to-1. It's 8.2 Ks and 10 Ks. One remark regarding the explanation of that circuit on Limpkin's website. There it states that the difference between the lower cutoff frequencies between the first bandpass filter and the second bandpass filter is intentional to eliminate any DC component that would remain after the first bandpass filter. However, I disagree. Because, that capacitor here would take care of any DC component coming out of this op-amp. And my best guess is that that slight difference is simply an artifact from having to choose some, existing values for all these resistors and capacitors. Second remark. I haven't drawn in the power supplies and filter capacitors for the OPA 2365, which is a dual op-amp audio preamplifier with very low noise and very high common mode rejection ratio, and the MAX 9031, which is used here as comparator. Third remark. If you look in the application notes of the HB100, you also find an amplifier circuit. And if you look closely at that part here, it's exactly the same as on Limpkin's amplifier board. Even the components of the passives have exactly the same value. That 330K resistor, the same value. However, Limpkin is using a much better operational amplifier. And he beefed up the power supply rails and that half VCC rail considerably. And he added that peak detector and, of course, the comparator at the output. I guess it's time now to meet two of these thingies up and see what they can do. I don't have to do a pan with the camera this time. I'm very slowly moving here. This is a Doppler radar. Anyway, I put now the HB100 module on the pin headers of the Limpkin breakout board. And the first thing we notice is we get a square wave signal out. And I don't know if you can see it. Let me zoom in. And I cannot point with the pen or my fingers to it because it will immediately disturb the signal. But what we have here, the yellow trace, of course, the frequency out at exactly 100 Hertz, which is incidentally the second harmonic of our mains AC 50 Hertz here in Germany. And above it, our V out, our signal level indicator, is not quite at 5 volts. It would be at 5 volts when it's at the very top. So that's the radar with no activity. Of course, if I start waving my hand here, our signal indicator goes up to 5 volt and we get a lower frequency square wave. So let's do that 21, 21, 21 again and see if we can get any stable frequency here. So let's see with the hand. 21, 21, 21, 21, 21, nice signal. 21, 22, 21, 22, 21, 22. And maximum signal level. Let's try it with the metal plate. 21, 21, 21, 21, and half speed. 21, 22, 21, 22, 21, 22. Oh, very nice. So, next step would be, of course, let me zoom out a little bit here and pan down. To connect a MCU and see if we can do something with that signal or with both signals. But maybe we should better do that in a second part. The video has gotten quite long as it is. And I plan to show you Limpkin's sample code for an Arduino, and maybe I will write my own code to analyze these signals with an Arduino, because reasons. Till then, bye.